Hello! In this video, we'll tackle an interesting problem involving binomial expansions and coefficients. By the end of this lesson, you will be able to first, find specific terms and coefficients in a binomial expansion. Second, apply the binomial theorem to expand expressions involving more than two terms. Let's start with the problem itself. The coefficient of x cubed in the expansion of the trinomial 1 plus 2x plus 3x squared, all raised to the power of 6, is equal to twice the coefficient of x to the power of 4 in the expansion of 1 minus x squared, all raised to the power of 5. Our goal is to find all possible values of the constant a. So, we have two separate expansion problems that we need to solve to find our final answer. Let's begin with the first part of the problem. Our objective is to find the coefficient of x cubed in the expansion of 1 plus 2x plus 3x squared, all to the power of 6. We need the coefficient of x cubed in the expansion of 1 plus 2 plus 3 by 2. This is a trinomial expansion. One way to approach this is to rewrite the expression as a binomial. Let's group the terms in the parenthesis. We can write it as the quantity 1 plus 2x plus 3x squared, all to the 6th power. By treating 1 as one term and 2x plus 3x squared as the second term, we can use the standard binomial theorem. Let's recall the binomial theorem. For an expansion of the form a plus b to the power of n, the general term, often called the t plus 1th term, is given by n choose r times a to the power of n minus r times b to the power of r. The letter r represents the position of the term in the expansion. In our case, a is 1 and b is 2x plus 3, 2, so we can write the general term. The general term, t sub r plus 1, will be 6 choose r times 1 to the power of 6 minus r times the quantity 2x plus 3x squared, all to the power of r. Since 1 to any power is just 1, the expression simplifies. The general term is 6 choose r times 2x plus 3x squared, all to the power of r. Our goal is to find values of r that result in an x cubed term. Now, let's analyze the general term to see how we can get an x cubed term. We have t sub r plus 1 equals 6 choose r times the quantity 2x plus 3x squared to the power of r. The important part here is the expansion of x plus 3 by 2 to the power of r. This is another binomial expansion that we need to perform for each possible value of r. We know r must be an integer between 0 and 6. Let's start with the smallest possible value for r. Consider r equals 0. The general term becomes 6. Choose 0 times 2x plus 3 by 2 set to 0. Anything to the power of 0 is 1, so we get 1 times 1, which is just 1. This is a constant term, so there is no x cubed term. Next, let's try r equals 1. The term is 6 choose 1 times 2x plus 3 by 2 at 1. This simplifies to 6 times 2x plus 3 by 2, which equals 12x plus 18 by 2. Again, no x cubed term here. Let's increase r to 2. The term is 6 choose 2 times 2x plus 3 by 2 at 2. Now we have something interesting. Let's expand the squared term. Expanding the inner binomial, we get 2x squared plus 2 times 2x times 3x squared plus 3x squared squared. This simplifies to 4x squared plus 12x cubed plus 9x to the power of 4. Look at the middle term. It's 12x cubed. This is what we're looking for. So when r equals 2, we get a coefficient of 6 choose 2, which is 15, multiplied by 12 from the inner expansion. The coefficient of x cubed for r equals 2 is 15 times 12, which is 180. We found one part of our answer. We found a contribution to the x cubed term when r equals 2. But we need to check if there are any other possible values for r between 0 and 6. Let's try r equals 3. The term is 6 choose 3 times 2x plus 3x squared cubed. This is more complex, but we can look for the x cubed term. The expansion of 2x plus 3x squared cubed will contain terms like 2x cubed, 2x squared times 3x squared, and so on. Notice that the smallest power of x will be 3 from the 2x cubed term. Any other term will have a higher power of x, like x to the 4 or x to the 5. So, for r equals 3, the x cubed term comes from 6. Choose 3 times 2x cubed. This gives us 20 times 8x cubed, which is 160x cubed. Now let's consider r greater than 3. For instance, If r equals 4, the term is 6, choose 4 times 2x plus 3x squared to the power of 4. The smallest power of x we can get from this expansion is 4 from 2x to the power of 4. Since the smallest power of x for r equals 4 is x to the power of 4, it's impossible to get an x cubed term. The same logic applies to r equals 5 and r equals 6, where the smallest powers would be x to the 5 and x to the 6, respectively. This confirms that we only get x cubed terms from r equals 2 and r equals 3. To find the total coefficient, we sum the contributions from these two cases. The total coefficient of x cubed is 180 plus 160, which equals 340. So, we've solved the first part of the problem. This coefficient is what we'll call C sub 1 for the first expansion. Great. Now let's move on to the second part of the problem. Our objective here is to find the coefficient of x to the 4th power in the expansion of 1 minus x squared, all to the 5th power. We need the coefficient of x to the 4th in the expansion of 1x squared to the 5th power. This expansion is more straightforward because it's already a binomial in the correct form. We can use the binomial theorem directly. Recall our formula. T sub k plus 1 equals n choose k times a to the n minus k times b to the k. In this case, n is 5, a is 1, and b is negative x squared. Be careful with the negative sign. Substituting these values into the formula, we get the general term. T sub k plus 1 equals 5. Choose k, times 1 to the power of 5 minus k, times the quantity negative x squared to the power of k. This simplifies to 5 choose k times negative x squared to the kc. We can distribute the exponent k to both parts inside the parenthesis. This gives us t sub k plus 1 equals 5. Choose k times negative a to the power of k times x to the power of 2 times k. We want the coefficient of x to the power of 4. To find this term, we just need to set the exponent of x equal to 4. So we set 2k equal to 4. Dividing both sides by 2, we find that k must be 2. This means the x to the 4th term is the 3rd term in the expansion. Now we can find the coefficient by substituting k equals 2 back into our expression for the general term. The coefficient, which we'll call c sub 2, is 5 choose 2 times negative a to the power of 2. Calculating this, 5 choose 2 is 10, and negative a squared is positive a squared. So the coefficient is 10a squared. Let's quickly recap what we've found so far. We determined that the coefficient of x cubed in the first expansion is 340. The coefficient of x cubed from the first expression is 340. And the coefficient of x to the 4th in the second expansion is 10a squared. The coefficient of x to the 4th from the second expression is 10a squared. The problem states that the first coefficient is equal to twice the second coefficient. Now we can set up our final equation. The equation is c sub 1 equals 2 times c sub 2. Substituting the values we found, we get 340 equals 2 times 10a squared. Simplifying the right side, we have 340 equals 20a squared. Now we just need to solve for a. First, we can divide both sides by 20. 340 divided by 20 is 17, so 17 equals a squared. To find a, we take the square root of both sides. Remember that the square root of a number can be positive or negative. Therefore, a equals the positive or negative square root of 17. So, we have found the two possible values for the constant a, positive root 17 and negative root 17. Let's quickly review the steps we took to solve this problem. First, we broke the complex trinomial expression down into a binomial by grouping terms. This allowed us to apply the standard binomial theorem. Second, we found the general term of the expansion and systematically tested values of the index r to find any and all terms containing x cubed. We found two such terms and added their coefficients together. Third, we found the coefficient of the desired power, x to the 4th, in the second, simpler expansion. Finally, we used the relationship given in the problem to form an equation and solve for the unknown constant a. This method of grouping terms in a multinomial expansion is a very powerful technique to remember. You can apply this same process for trinomials, quadrinomials, and so on. I want to briefly show you a more formal but less intuitive way to find the coefficient of x cubed in the trinomial expansion. This is called the multinomial theorem. The multinomial theorem states that for an expansion with k terms, the general term's coefficient is n factorial, divided by the product of the factorials of the exponents, times the product of the coefficients of the inner terms raised to those exponents. Here n was 6, and our terms are 1, 2x, and 3x squared. So for our problem, the coefficient is 6 factorial over p factorial, q factorial, r factorial, times 1 to the p, 2 to the q, and 3 to the r. The condition for an x cubed term is that the sum of the powers of x from the terms in the expansion, which are x to the q and x to the 2r, must equal 3. So q plus 2r equal 3. We also know that the exponents must sum to 6p plus q plus r equals 6. Now we just need to find all combinations of non-negative integers p, q, and r that satisfy both conditions. If e equals 0, then q 3. Since p plus q plus r equals 6, p equals 3. This gives the combination 3, 3, 0. If r equals 1, then q equals 1. Since p plus q plus r equals 6, p equals 4. This gives the combination 4, 1, 1. If r equals 2, then q equals 1, which is not allowed as exponents must be non-negative. So these are the only two combinations. Now we substitute each combination into the multinomial coefficient formula. For 3.3 fusion, we get 6 factorial divided by 3 factorial times 0 factorial, which is 20 times 2 cubed, which is 8 times 3 to the 0, which is 1. This gives 160. For 4001, we get 6 factorial divided by 4 factorial times 1 factorial, which is 30 times 2 to the 1, which is 2 times 3 to the 1, which is 3. This gives 180. Adding them together, we get 160 plus 180, which is 340. This is the same answer we found using the grouped binomial method, confirming our result. While this method can seem more structured, the previous method can be more intuitive for many problems. Both are valid ways to solve the problem. So we've come to the end. Let's recap what we have accomplished in this video. We successfully found specific terms and coefficients in both a binomial and a trinomial expansion. We applied the binomial theorem to expand expressions involving 3 terms by grouping them into 2. And, by solving an algebraic equation, we found all possible values for the constant a. The final answer to our problem is a equals positive or negative square root of 17. So a is plus or minus the square root of 17. Thank you for watching.